Hi guys, I hope you're doing well. This is our third lesson for Unit 4, and this is all about probability distributions. And so the next couple lessons will get a bit more complex than that last one, which was uniform probability distributions. But it definitely follows patterns, and it's a bit more predictable, I think, as long as you can identify what kind of probability distribution you have. So today we're going to talk about what's called binomial distributions, and there's lots of situations in probability where you can think of them as having just only two possible outcomes. And you can often think of these as just being viewed as success or failure, or let's say winning and losing. Anytime you can classify things into this situation, we call it a binomial distribution. So lots of things where you have things like a quality control inspector, the thing's either going to pass the inspection or it's going to fail. Lots of things, like in sports, you're either going to score or you're not going to score. And so anytime you can make it all about two different outcomes, and even when you're rolling dice, you can say, okay, what's my probability of a 7 or there not being a sum of 7? And so those are situations where you can think of having just two possible outcomes. So I'm going to use the example of a hockey player taking a penalty shot. And so a penalty shot is just one player who goes in on the goalie. And so there's two possible outcomes, either success, he scores, or failure, he or she doesn't score. And so there's one hockey player who was famous quite a few years ago now, but his name was TJ Oshie, and he has one of the highest percentage of scoring when he goes on penalty shots. And so he's just over 50% of scoring on any penalty shot opportunity. So we can think of this as being the probability of success. So this is my probability of success or of scoring. So we're going to look at kind of a trend here to get a general rule. So the first one, it says, what is the probability that he scores twice on two shootout opportunities? So this one's not too complex. So the probability of two goals. So it's going to be the probability that he scores on the first one, so 0.518, and then the probability that he scores on the second one, multiplied together. So just like that, so we can think of that, I'm just going to write it this way, 0.518 squared. So that comes out to approximately 0.268. And we would expect the more times he's going to score, if there's less probability that that's going to happen. And so in the second one, it says, what's the probability that he scores exactly twice now on three shootout opportunities? So this gets a bit more complex because he could have, let's say, goal and then score again, a goal, and then let's say he doesn't score, so it's a save, like that. So G is goal and S is save. But he could also have it as he doesn't score on the first one, and then he gets a goal and then a goal. Or he could have it where it's in the middle, where he doesn't score on the middle one. But the key here is to recognize that we have different ways we can arrange the success within the three opportunities. And so when we do this, the probability of scoring, so two goals on three shots, is equal to, just like we had before, the probability of scoring. And because we're doing it twice, it's going to be squared. And then the probability of not scoring, which is the same as, if I figure it out here, 1 minus the probability of scoring. And that's to the exponent 1 because we just have one time where we're not scoring. What we also have to include here is this stuff. I know I'm going to have three different ways I can do this. How you can write this is using combinations. This is like having 3 choose 2. Or the way I would probably write it is just 3 choose 2 like this, which comes out to different arrangements that you can have 3 items when you're only picking 2. And so I get this number of 3. And so that's going to be the thing I'm going to put in here. I'm going to have the 3 choose 2 here. And so if I work this out, this becomes 3. I'll leave this one as that squared. And then my probability of not scoring or of failure goes there. And so that I get a value overall of 0.388. So a better opportunity than if he just scored on 2 out of 2 opportunities. He's getting an extra chance to score. And so in here, again, and hopefully recognize here that the probability of not scoring is simply 1 minus the probability of scoring. But if we look at another one here, so what's the probability that he scores 2 times on 4 shots? And so again, we still need to include all of the different arrangements here of 2 goals and also 2 saves from the goalie. And so this is what we want to include. So I got the probability of 2 goals on 4 shots. And this is where I want to include my combinations of 4 choose 2. And notice here I've got 0.518 squared, and then my probability of not scoring also squared because it's twice. And so this works out to approximately 0.374. And so we can kind of look at a pattern here. And this is what I want you to see why we kind of did this multiple times, is that there's a few things going on. And one is that notice here, whatever I had for the combinations that I'm choosing is equal to the number of successes. And so that goes into my success times success, or in this case, twice for that example. Here, similarly, I had 2 and 2. So that's one pattern that happens. The other is that my overall number here that I'm choosing from, so I had 4 shots, that means my exponents here added up to 4. Here, I had 3 shots and my exponents added up to 3. And so we have this general situation that we can, anytime we have some sort of binomial probability distribution, I can always set it up like this. And so I say it's the probability of whatever we're talking about, x, where x is the number of successes. So I have the total number of trials, or whatever we're talking about, choose the number of successes, where p is the probability of success, and x is the number of times it occurs. And then I have 1 minus the probability of success, which is the probability of failure. And then whatever's left over from the total number of trials minus the number of successes is going to be the exponent there. So another way to write this could be, you could change your combinations, the same thing. So combinations of n choose x, which is what I think the textbook does. Probability can stay the same, but sometimes people prefer to write in q, where q represents the probability of failure. And you have that number there. I'm just going to put that back to blue. And so this is a general formula, and you can pick which one you want, that's going to always work for some situation where you have a binomial. And we'll do some practice here that's going to help out. So x is the number of successes. And n is the total number of trials. P is the probability of success. And Q, if you choose to include it, which is 1 minus P, is the probability of failure. Or whatever you deem to be whatever the other thing is. It doesn't necessarily have to be a failure situation. So what's going to be important is to be able to distinguish when you have this situation versus when you have something else. So in a binomial experiment, you have to have always n identical trials. And so what that means is that your probability is never going to change as you go and continually go through these trials. So each trial is exactly the same. And so it kind of relates to what we talked about in the previous unit, where you have things that are independent versus dependent. So all the trials are independent. And again, as we said, there are two possible outcomes termed success and failure. And the probability of success is P, and the probability of failure is 1 minus P. So let's look at some examples where we can have this happen. So it says dice are rolled 20 times. What's the probability that double sixes are rolled exactly twice? So we've got dice rolled 20 times. What's the probability that double sixes? So first thing to recognize is that double sixes is really just the sum of 12. And so if we start to identify what we have here, so the first thing is dice are rolled 20 times. So that's like the number of trials. So my N is 20. And my number of successes, if I talk about X being the number of successes, X is that if I roll double sixes or a sum of 12, exactly twice. And then my probability of success, so my probability of sum of 12, so hopefully remember that that's going to be 1 over 36. And then 1 minus P is going to be then 35 over 36, like that. So you have everything you need, and even if you don't remember the formula, I think you can always come up with this. So I can have these sum of 12 twice in any of the 20 times that I roll the dice. And so I have to use my combinations of 20, choose 2. And then I've got 1 over 36 to the exponent of the number of successes. So I want that twice. So the probability of getting the sum of 12, 1 over 36, I have that twice. And then everything else is going to happen the rest of the time. And so out of the 20, if I take 2 away, I've got 18 left for my failure situation. So all I have to do is plug that all in, and I get 0.088 approximately. So that gives me the probability that I'm going to get sum of 12 twice in 20 rolls. So another example, it says, consider a game where a coin is flipped 5 times. You win the game if you get exactly 3 heads. Why don't you try this one? I would pause the video here and see what you get based on this. So I'm going to write this out, so hopefully you've paused it. So my number of trials is 5. Probability of success is 1/2. That makes 1 minus P also 1/2, so that doesn't change anything. And then I want exactly 3 heads, so X is 3. So I've got 5, choose 3. 1/2 to the exponent 3, and then it turns out, because this one's a uniform probability, I really could have done that to the exponent 5, but it doesn't matter. It's going to work out the same. So if I plug that in, I get 0.313. So hopefully you're able to get that one. So the next one's a bit trickier. It says, suppose the game is changed so that you win if you get at least 3 heads. So what's the probability of winning in this case? So at least 3 means you could have 3, 4, or 5 heads. So I have 3 different situations where I have to figure out the numbers. So I want the probability of 3 plus the probability of 4 plus the probability of 5. So the probability of at least 3 is going to be those situations added together. So we just did the probability of 3, so I'm just going to put that one in. So I've got 0.313. Then I need this one. So similarly, I've got 5, choose 4. 1/2 to the exponent 4, and then 1/2 to the exponent 1. And you could just, again, simplify that to the exponent 5 if you want. And then 5, choose 5. And then like that. 1/2 to the exponent 5. So if you work that out, you get approximately 50%. And so the flip of that, you could do this as the complement, where you go 1 minus the probability of the opposite, which is would be the opposite of 3, 4, and 5, which is 0, 1, and 2. So it ends up being a bit more work to do the opposite, but you could do it that way as well. So this is a kind of example where it leads to the fact that you could actually just find all of the probabilities and hence get a probability distribution. So that's what we're going to do here. We've already done some of the math already, so that's going to be helpful. So it says tabulate and graph the probability distribution for the number of heads in the tossing of a coin 5 times. So you have to think of what the outcomes would be, which is X here. And that's the number of heads. And so it's really important not to forget that you could have a situation where you have no heads, or all 5 situations would be tails. And then you have 1, 2, 3, 4, and 5 number of heads. So to calculate those, we have to use our formula. And I'm going to, just because it's, actually, maybe I can, I'll do it this way. I've got 5, choose 0, and then all the probability of my tails, like that. And then 5, choose 1, 0.5. And I'm going to write them separate, even though you could put them all together as 0.5 to the exponent 5. But just so you see it in your notes like this. And then I've got 2. And again, why don't you just pause the video and see if you can come up with the rest. It's, hopefully it's intuitive, but just so you have that practice of getting these. So if I want 3, that's going to be my exponent here, and then that one becomes 2. And then 4 and 1, and then my last one. And so if you were to punch those all in, and this, if you want, you can just copy off of the screen here. There's my probability. Oops. And so I get all of my probabilities there. And notice here, my 2 largest probabilities, here and here, are the probability that I get 2 heads or 3 heads. And it kind of makes sense if you think about it logically. This is like the highest chance that it's going to happen. It's more likely that you're going to, because this is a 50-50 chance, get the middle number within the distribution. And again, one thing to note is that if you were to add all of these probabilities up, your total will be 1. And so it's all of the possibilities that can happen in this situation. So if I graph these, so I've given you your various probabilities here. So this would be the probability of getting 0, 1, 2, 3, 4, and 5. And this is X, which is the number of heads. And this is my probability of X. So if I go back up, 0.0312. So it's kind of an estimation here. So that's about there, 0.15. Roughly there. And it was at 0.312. And that's the same for these two. Oops. And then it evens out, it's symmetrical over here. And so there's my probability distribution for these. And you'll notice this starts to look like a bit like a normal distribution. Okay, so again, other things you can do with this situation, you can also figure out the expected value just like we've done in the past. So the expected value of a binomial that consists of n trials with the probability of success p is pretty simple. We're just going to have the expected value is equal to the number of trials times the probability of success. And again, it's going to make sense if you think about the situation. So if we go back to our first example, which was the hockey player, it says, what's the expected number of goals for Oshie on 5 penalty shots? And his probability of success was this 0.518. So I would have the expected value equals the number of trials. So in this case, n is going to be 5, and our p we just said is 0.518. So I've got 5 times 0.518, which gives me approximately 2.59. So we would expect them to be between 2 and 3 goals on any 5 shots. And so pretty straightforward. So last one here is a situation where we need to use the complement and think about it that way. Again, you could try this on your own. So it says, in a manufacturing process, it's estimated that 0.1% of the products are defective. If a client places an order for 25 products, what's the probability that at least one of them is defective? So I'm going to write down a few things that we know. So my probability, if we want to think of success here as actually the opposite, being defective, is going to be 0.001, because that's 0.1%. So that's my probability of being defective. And then 1 minus p is going to be 0.999. And then I've got n, which is 25. I'm going to leave x out for a second. So if I want to think of the probability of at least 1, I can also think of the probability of at least 1 being 1 minus the probability of 0 defective. And so that's going to be much, much easier than if I tried to figure out, probability of 1, 2, 3, 4, all the way to 25 separately. So if I plug that in, I want to think of, in this case, my probability of 0 defective. So that means in this one, my x is going to be 0. So I have 25 choose 0 times the probability of defective, which we said was 0.001, but I have it to the exponent 0. So you could actually leave it out. And then all of them, in this case, are going to work. So I've got 0.999 to the exponent 25. And I can plug all those in and do 1 minus. So this number keeps going. So I get approximately 0.247. So again, what's the probability that at least one of them defective? So it's a bit less or a bit more than 2%. So therefore, probability that at least one is defective is 0.0247. Okay, so hopefully you get some practice with that. Here's the assigned questions. So there's some good ones to go through there. But of course, if you have any questions, just let me know.